All right, today we're going to cover topic 6.3, talking about Riemann sums and integral notation. And the first thing I want to point out to you is the Greek letter sigma stands for sum. All right? And when you see this thing with the n up here and k equals 1 and we're summing up a sub k and this looks all scary, it just means that we're adding up all of these things that are right here. We're adding up a sub 1, we're adding up a sub 2, and a sub 3, and a sub k. And the way that that fits into what we've done the last couple of days is we have added up all of these areas. And if you remember how we've done it, we have taken a function value. Let's say that we were doing the very first one at the left edge, and we call that x sub 1. And then we multiplied it by the width. And then we added it to the function value at the left edge of the next rectangle. We'll call that x sub 2. And we multiply that by the width. And then we did the third rectangle, and we did f of x sub 3, and it was times the same width. All right? So you can see why we're talking about this idea of a sum. Here we have a sum. All right? So we could have taken this thing that we just wrote right here, and we could have written it as a sum. We could have said that it is the sum of f of x sub k times the width. All right, we could have written it that way. All right, and we could have said that k equals 1, and then we put our n up here. Our n, if we were doing 4 rectangles, we would say something like n equals 4. We'd put that up there. All right? Now, what we said is that this width is called delta x. It is the change in x from our graphs. If you remember, we took our graphs and we had a little graph up here, and we divided it up into all these rectangles, and we said that this width of the rectangle was the change in x, or delta x. All right? So that leads us to this more complicated page here, but now it makes a little bit of sense to us. F of c sub k, this thing right there, that's all our function values that we just talked about. Here's our delta x. Here is us adding them all up. So all of that should look familiar. Now, what you notice is this new piece right here, this limit piece. When Sir Isaac Newton was developing the calculus, he decided that we were going to let the number of rectangles go to infinity. And if you let the number of rectangles go to infinity, then it is technically a true integral. All right? So, all we do when we see this symbol, this big, long, it is actually an elongated Roman letter S. It still just stands for sum. All right? All we are doing is we are summing up. We are adding up. And here's that sum symbol again. We are adding up all of the areas of those rectangles, just like we talked about on the first page right here. And so when you see this notation right here, it is just referring to adding up all of the areas of those rectangles. Now, this piece right here we talked about the last 2 days, that delta x is equal to b minus a divided by n, and n is the number of subintervals or our number of rectangles. All right? So, let's keep moving here. This is just kind of a picture that gives us a little bit more detail, but I want you to notice something in this picture. It leads us into this a little bit more complicated expression right here. And this expression right here that I underlined shows up in some AP problems. And if you understand the expression, it's not as bad as it looks. All right? But look down here at our graph. Okay? I have f of a plus f of a plus delta x. All right? And so what we're talking about, my delta x right here, it doesn't change. It's still this piece that it always is. All right? But my function values depend upon wherever I'm starting at and then what I'm adding to it. So in this first rectangle, this x value right here is going to be a plus the change in x. Well, when I get to this one, it's going to be a plus 2 of those. When I get to this one, it's going to be a plus 3 of those. All right, so that's all that this thing means right here. Okay, and we'll use this again in just a minute. All right, so and once again, our delta x refers to dx. Back on this, I'm not sure that I pointed that out real well on this slide here. Delta x is changed to dx. It's referring to that really, really small width. See, if I let the number of rectangles go to infinity, up here, I only have 3 or 4 rectangles. But if I let those number of rectangles go to infinity, then the width becomes almost a non-issue. All right? And so it is just represented by that dx, which is just called the differential. All right? So let's look at this problem that kind of deals with what we're doing in topic 6.3. Interpret the definite integral as the limit of the Riemann sum. Interpret the definite integral as the limit of the Riemann sum. So what we're going to do is we're going to turn it back into our kind of sigma notation. Okay, we're going to take, let me get a good color here. We're going to have the limit as h approaches infinity. Put our little sigma symbol in there. Put my k equals 1. I'm going to have f of c sub k delta x. All right. Now, what I want you to notice is this is just our rough form here. What we need to do is we need to get our limits of integration. We need to do something with these limits of integration. So what this thing is saying is that we are going to find the area under the curve from 3 to 8. All right? From 3 to 8. So my width, that dx, is going to be b minus a over n. Well, I know my b and my a. There's my b and my a. So it's going to be 8 minus 3 over n, which is 5 over n. That is my width, and that is the same thing as my delta x. So I just put that in right here. So I'm going to have a 5 over n right here for the delta x. None of this over here is going to change. This is still the limit as h approaches infinity. We're letting the number of rectangles go to infinity. All right? And now I put the function in right here. So I'm going to have 2 times x minus 3, the quantity cubed. Now, one thing that they do that I'm sure is a little bit annoying to you is they like to label all of these x's, and so they put a little x sub I down there. I'm doing that because you will see it in AP problems, and I don't want it to, mess you up. It's still notice it's still the same function. They just put a little I right there. All right, so don't let that worry you. And that problem is done. This right here is my answer. Okay. Now let's go on to our next problem. This problem here is, again, not near as bad as it looks. Express the limit of the Riemann sum as the definite integral using the lower limit a as a equals 0 and then as a equals 2. All right, so what I want you to notice is that they've given me this thing right here. This 7 over n is standing for my b minus a over n. All right, so the first thing we do is we take our a equals 0 and we put it in for there. So when I do that, I have b minus 0 over n. Okay, and that has to be equal to 7 over n. So what does b have to be? b has to be 7. b has to be 7. So now we can actually write our integral. All right, and that's all they're wanting us to do, is to write this in integral form. It's going to be the integral from 0, which they gave us, to 7, which we used this little thing to get to the 7, all right, of my function 4x to the 5th dx. All right. Now, what if, I'm going to insert a page here. We didn't do the other part. This part requires a little bit more thought. What if a equals 2? Remember, this problem said do it with a equals 0, and then it said do it with a equals 2. All right. This one is a little bit more squirrely, but it's not real bad. Okay, if a equals 2, I'm still using this b minus a over n thing, all right, and it still has to equal 7 over n. So if I put a 2 in, for a, then I have b minus 2 over n equals 7 over n. And if I take this top part, 7 equals b minus 2, I find out that my b value is 9. All right? So we now know our limits of integration. Our limits of integration are going to be from 2 to 9. But we need to shift the function right, okay? The interval was shifted. The interval was shifted right 2, so we need to shift the function right 2. So instead of just using regular old 4x to the 5th, we're going to use what we know about transformations, and we're going to make it 4 times x minus 2 to the 5th dx. And that's what makes this problem a little bit more tricky. All right. take a look at this problem, which looks a lot worse than what it is. All right, they're asking us to rewrite this thing here as a definite integral in terms of h of x with a lower bound of x equals -1. So we're going to turn to our old friend again. The width equals b minus a over n. And we're going to put in, this is the lower bound, so I'm going to put it in for a. So that's going to be b minus a -1 over n. And look what it's equal to. It's equal to my 5 over n. So now I can set the numerators equal to each other. 5 equals b plus 1. So my b value must be 4. Well, we're already doing good. I know my limits of integration are -1 to 4. All right? And I just have this function. This thing in here looks really scary, but in reality, if you come back to our definition, the limit as n approaches infinity of my sum value of f of a plus delta x times k that I showed you a minute ago times the delta x, you can see that this thing right here, all right, is just represented right here, all right? So, long story short, this is just that. It's just h of x dx, all right? And so that problem looks really bad, but in reality, it's not that bad at all. And so we are going to stop there for today with topic 6.3.